Hello and welcome to another video. Today we're going to be working on 0, 1 matrix. In this problem, you're given an n by n matrix, and you want to return the distance of the nearest 0 for each cell. The distance between two adjacent cells is 1. So in this first example, every cell that already has a 0 is going to have distance 0. So all of these are just going to have 0, 0, 0, 0, 0. And then 1 is one distance away from all of these. So then what we need to return for this one, this needs to be a 1 here. And that's essentially what we're doing. So we're returning 0, 0, 0, 0, 1, 0, and 0, 0, 0. So it's the same matrix as the zeros. Now let's look at the second one. So every single 0 that is already a 0 is going to be 0 distance away. So these are all going to be 0. So let's just write those in as our output values. So this is going to be 0, 0, 0, 0, 0. Because a 0 is 0 distance away from a 0 value because there's literally 0 in there. Now let's look for these. So this one is 1 distance away from these, so it's going to be 1. This is also 1, and this is 1. And now finally this one is 2 distance away, and it's also, so you can kind of tell, like, anytime there's already a number, this is going to be the intuition for the problem, and anytime there's already a number in one of these, and you're looking for something else, you just look for, okay, what am I closest to, and what's the smallest one of those, right? So because these are all 1, this is going to be 2. It's the smallest one of those plus 1. So let's actually figure out how we can do this problem. And what we're going to use to figure that out is a matrix as well. But we're going to have a 3 by 3 matrix. And we are just going to only have zeros. Or, sorry, we're going to have 1, 0. So let's do that. So we're going to have a matrix here. This. As always, my lines are pretty bad, but... And what we're going to do is we are going to have a value here, and we're just going to use like maybe green. And so our matrix is just going to have all 0, or like this. So it's going to be a 0 and then all 1s. And let's actually, before we do that, I think we want to copy that. So hopefully it lets me do this. If I actually copy it, yeah, perfect. There we go. So we're going to have a matrix on the left with our numbers. And so our numbers are just going to be 1, 0, and then all 1s, just to show what we're doing. Better example. And now here, what we're actually going to do is we're going to initialize everything, and we can just initialize everything to -1 or something. You could do whatever you want, though. Okay, so we're going to initialize all these to -1. And we are going to use a visited set, but you don't necessarily have to. It doesn't really make a difference. Your space is still the same because we are also going to use a deck to store the numbers. So essentially what we're going to do is we're going to, every time we're at a 0, we're going to put that into our deck. So let's also draw out these indices. So this is 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2. Okay, and then let's also draw out our deck. So for our deck, we're just going to have an array down here, but it's basically a queue. And then what we're going to do to start off is we are going to go through this left thing. This is our matrix. Call that mat, and let's call this result. Okay, so what we're going to do is we're going to go through this left side first, and we're going to just go through this, and every single node that's a 0, we're going to mark it as a 0 because a 0 is 0 away from each other, and so we're going to mark those as visited. So let's go through this. So for here, there's only 1 0, and that's over here. So we're going to change this value to a 0. And now what we're going to do is we're going to add that to the queue, and we're going to mark it as visited. So that's going to be 0, 0, 0. There we go. Okay, perfect. So now what we need to do is we need to pop it from the queue, right? We're going to keep popping from the queue as long as there is a queue. And this V is going to symbolize visited. So we're going to pop this from the queue. But before we do that, we need to add, we're going to pop it, and we're also going to add the nodes next to it. So, but we have to check the nodes next to it, and we have to also update those values. So we have to check in every direction. This is out of bounds. This is out of bounds. We need these 2 nodes right here. Okay. So these 2 nodes, what should their value be? Well, it's whatever this value was plus 1, right? Because they are 1 away. So these 2 nodes should have value 1. And now we need to add them to the queue, and we need to get rid of this node over here because we just popped it. Okay, so let's add those nodes to the queue. So 1 is 0, 1, 1. Doesn't matter what order you add. And then the other is 1, 0, 1. Okay, now we're going to look at this node here. And so this 0, 1, 1 is row 0, column 1, which is this one over here. Now we're going to do the same thing. We're going to mark it as visited. And then we are going to, so actually, sorry, as soon as we add a node into the queue, we need to mark it as visited. So these were already visited. Yeah, because they were already in the queue. Okay, so now for this node, we need to check every direction. So here we are, I guess we can look here. So here we're out of bounds, here we're visited already. So we need these two nodes over here, this node and this node. Okay, and what should their value be? Well, it should be whatever that value was plus 1. So 1 plus 1 is 2. So these two nodes should have value 2. So 2, 2, and then we need to add them into the queue. So let's do that. So these two nodes, one is 1, 1, 2, and the other is 0, 2, 2. Okay, now we are going to get rid of this node from the queue because we popped it already, so technically should have been gone. I just left it to show. Okay, there we go. Now we are going to be at this node, 101. So 101 is this node over here. So we're going to do the same thing. We're going to check the directions, and we are going to say, okay, well, and we forgot one more thing, actually. Since we added these two nodes to the queue, we needed to mark them as visited. So there we go, right? These two nodes over here. Okay, so for this 101, it's over here, and we need to check, okay, well, where can we go? So this is visited, this is visited, this is out of bounds, and this is the only node, this is the only new one. So we need to add this node over here, and we need to figure out what value to change it to. So remember, it's going to be whatever value we had plus 1, so that's going to be 1 plus 1, so that's going to be 2. So this is 2. And then we need to mark that node as visited, and then we need to add it to the queue. And the reason we can mark it as visited before actually visiting it, right, when we append it to the queue, is because all of these like paths are one distance away. So you can mark it as visited right when it goes into the queue, because if you essentially have this node, and then you have the same node farther down the line, you're going to reach this one first all the time. So you can just mark it as visited right away. Now, if this was a graph and the path links were different, then it would be different. But because this is a queue where everything is the same distance away, you can just add it to the visited right away. Okay, so now we need to add, kind of forgot where I was at there. So we added 0, 2, 2, let me just go back 1 second. 1, 0, 1. Yeah, let me go back a little bit here. So 1, 0, 1. Oh, no, I think we're good. I think we're good. Yeah. Okay, so essentially what happened is we need to add this node over here, right? And so this is row 2, column 0, and value 2. And then we can get rid of this 101 node because we've just looked at it, right? 101 is over here. So we can get rid of that because we just used it. Okay. So now this is what we have. I think this is correct, hopefully. So 112 is over here. And now we need to do the same thing. We need to check. Oh, by the way, I forgot to mark this one as visited. So for 112, we need to check the same thing. So this is visited, and these two are good. Now, what should that value be? Well, that should be 2 plus 1, so it should be 3. So let's do that. And you see, like, as we're visiting these nodes, the first node you visit is going to be the smallest possible number. So that's why the queue is good. Okay, now we need to mark both of these as visited, and we need to add those to the queue. So let's do that. So this is 2, 1, 3, and this is 1, 2, 3. Yeah, okay. And then we can get rid of this node. Let's do that. So now every node is visited except for that bottom right one. So 0, 2, 2, where are we here? So 0, 2, 2 is row 0, column 2, so it's over here. Yeah, it's that one here with a value of 2. So here, everything is visited. So this is visited, and these two are out of bounds. So we don't actually do anything. We just get rid of the node. So we'll get rid of that node. Then for 202, where is that? So 202 is this one down here. And everything is also visited, right? So visited, and out of bounds. So we don't need any of those. So we can get rid of that one too. And for 213, so where's that? That's actually here. And so this is visited, this is out of bounds, but this is a value. And what should that value be? Well, it should be 3 plus 1, so this should be 4. And then we're going to technically need to add this node to the queue, but as you can see, like, now that everything is visited, now every node you're going to visit, everything else is going to be, so technically if you wanted to add this node, you could add 224, but now essentially every single node is going to have no adjacent nodes, so you're not going to do anything else. You're just going to pop this, you're going to pop this, find nothing, and pop this, find nothing, and then you'll have an empty queue, and then finally you're going to have a matrix that is what you want. And does that make sense? Like, if you think about it, like, these are 1 away, these are 2 away, and this is 3 away, and this is 4 away, which is what we wanted. So that's our algorithm essentially. We're just making a type of walls and gates thing where instead of looking how far it is from everywhere, we're just putting all our zeros into a queue, and we're guaranteed to have at least 1 0. So we're putting all our zeros into a queue and just searching everywhere. And then we are making sure not to go to the same place twice by doing. You could do one of two things. You can either have a visited set, or you could take out the visited set. And like, let's say you make all these -1, you could just say like, okay, if this value exists and it's not -1, then I probably don't want to put it into the queue again because I've already used it. So either one of those works. And the visited set doesn't actually add any space complexity, as we'll show later. It might be a little bit slower on LeetCode in terms of space, but it's a little bit more convenient. Okay, so let's write our code now. So first of all, we're going to have a rows and a columns, as always, for these kinds of things. It's going to make it a lot easier. And this is at least a 1x1 matrix, so we don't have to check like if it's if none of these are equal to 0. We don't have to check for any of that. Then we're also going to have directions, which is also really useful. And that's just going to allow us to look in every single direction very quickly. So we're going to have 0, 1, and -1, 0, and finally 0, -1. Okay. Now what we need to do is we need to actually make our result matrix. And so we're going to do a list comprehension there, and we're just going to make -1 for every value. So we can just say -1 for, and if you don't really care about the I value, you can just leave it like this. It's like you can leave it blank. So we're going to have a array of length columns, and we're going to have rows of those. So we're going to say nested matrix there. And yeah, we don't really need these I values, so we can just leave it blank. Okay, then we're going to have a visited set. And finally, we're going to have a zeros deck. And essentially, yeah, the reason you can have a visited set and it doesn't cost you anything is because we're going to have the zeros deck anyway, which is going to be n by m. So it's not adding any space complexity. Okay, so now remember, our first step is we need to go through the matrix, and we need to take every single 0 and actually add it into our deck and put it in visited. So let's do that. So we're going to say for row in range, and this is why the rows and columns are really convenient. You can reuse them a bunch. I would definitely recommend making those. Okay, and so we just need to check if it's actually 0, not res, a row. So if this is 0, then what do we need to do? Well, we need to actually update our matrix. So res, did we? Yeah, we did have a res, okay. So res row column equals 0, because a 0 is 0 distance away from itself. Then we also need to add it to the deck. So 0.append. Then remember, we're going to have a row, a column, and a distance, and distance is going to start off as 0, and we're going to add it to the visited set. Row and column. Okay. Yeah, I think with the visited set, it makes it a little bit easier to read. It makes the time complexity. The time complexity is technically the same, but it'll make it a little bit faster in practice, but it makes the space complexity a little bit slower in practice, so it's kind of like a trade-off. Okay, so while our deck has stuff, what do we need to do? Well, we need to pop something. So we're going to say row column distance equals zeros dot pop left, popping from a deck. And then we need to actually go through the directions. So we could say like for RC in directions, let's make our new row and new column. So we could say like n row, n column, whatever you want, equals row plus R, col plus C. And then finally, we need to check if our, like whatever our new row and our new column is, if it's actually in bounds. So that's going to be if 0 is less than or equal to n row, which is less than rows. So this just means like, is our row not negative, and is it less than rows? And also the same thing for the column. So n column is less than columns. And then finally, you need to check, have you been in your visited set, right? Is it already in our visited set? In which case, we don't have to do anything. So in row and column, not in visited. And if all these things are true, then we can go through with our algorithm. So what we need to do is we need to say res new row is actually an n row and column. And what should that value be? Well, remember, it should be the old distance plus 1, right? We need to add it to our visited set. And row, and then we need to add it to our deck. And like I said, we can add to our visited set right when we add to the deck because we're guaranteed to hit that first, because everything is 1 distance away. So we need to add it to the deck, and we need to add an array here. So it's going to be n row, n col, and this plus 1. And so this should technically populate your entire res matrix. So now we just need to return it, and hope we don't have any errors. And we do. And we have more. Let's see here. We have one. Looks right to me, but let's just double check. Invalid syntax. Oh, it's because I never had it equal. Okay. How about now? List indices must be integers or slices. Yeah, so this is a mistake too. Like this. Okay, hopefully we're out of those. Nice. Okay, and it did work, it looks like, and it's reasonably efficient. So yeah, if you want to make the space a little bit more efficient compared to the LeetCode solutions, you can just take out the visited set. Or you could probably do it in place, but that's not like super recommended. So that would be like, oh, one space. I guess if you take out the visited set and do it in place, but you're not always allowed to do that. It wouldn't be too bad, but yeah, you could definitely do that if you wanted to. And the way you would do that in place is, it would actually be pretty straightforward. You would just go through this, and then you would, like, what you would do, yeah, I think the way you would literally do it in place is you would go through your original matrix, and then you can just say, like, for everything that's not a 0, or for all the zeros, add them to the visited set, do all the same stuff. And then for everything that's not a 0, you can either change the value. Like, as you can see, we're never really checking for -1, so you don't even have to change the value, technically. Like, I think if I made this whatever, it would still work. Like, we could try it. Like, I could make it like this. I think it would still work. Yeah, so you don't even have to change the values. You would literally just go through your matrix and then just add every single 0 into the deck. And then if you don't want to do the visited set, that's fine. Then you might want to change like the 1s to -1s or something, just to use that as visited, because then you'll know if you've been there before. That'll make it easier. But yeah, essentially you could do that, but you're not always allowed to override the input. So if you did it that way, it would be O of 1, but that's not always allowed. So in this case, I didn't. But it wouldn't be like it wouldn't be hard to do. Okay. So for the time, this is n by m, because we are going through the entire matrix, I guess, a few times. And since we have a visited set, I think this would technically be roughly n by m overall, because essentially every time you visit something, you're never visiting it again. So that would be n by m. Okay, and for the space, in our situation, ours is n by m. You can make it better by getting rid of a visited set, or you could also do it in place in the matrix if you wanted to. That's just preference. But yeah, that's going to be all for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.